Hello, you are watching Bold Science with Firuza. Today, we'll continue exploring what makes a hypothesis genuinely scientific rather than just a nice-sounding idea. The first criterion, falsifiability, was discussed in the previous video. The link to that video is located in the upper right corner of the screen. Briefly, a hypothesis must give reality a chance to say no. Now we move on to the second criterion, one of the most elegant and most unforgiving, the criterion that forces a hypothesis to predict the future, not merely sound persuasive. This is where a huge number of so-called theories fall apart. Let's begin. Criterion number 2. A hypothesis must make predictions. This is my favorite criterion. A good hypothesis is always a bit prophetic. It must say something like this. If you take specific equipment and perform a specific experiment, you will observe a specific new effect. In a real experiment, we must actually see that effect. But if a prediction refers not to present-day science, but to some distant future, then it's not science. It's an empty promise. There is a well-known Eastern parable. Nasreddin promised a sultan that he would teach a donkey to speak in 20 years. Why so long? Because in 20 years, either the donkey would die or the sultan would, and there would be no one left to check. That approach is unacceptable in science. No test indicates. A working hypothesis must produce testable prediction in the near future, within 2 or 3 years. A classic example of a properly formulated scientific hypothesis is the claim that a photon's frequency decreases as it moves upward in a gravitational field. Physicists Robert Pound and Glenn Repka tested precisely this statement. They formulated the experiment as follows. If gravitational redshift exists, then a gamma photon rising by 22.5 meters must lose frequency by a precisely defined amount. According to the formula, the relative shift is equal to gh over c squared, approximately 2 times 10 to the minus 15. If the effect doesn't exist, the frequency will remain unchanged. Here, everything is strictly defined. The height is specified. The direction of the shift is specified. The exact predicted magnitude of the relative frequency change is given, and null result is explicitly stated as the control. The experiment produced exactly the result predicted by the existence of gravitational redshift. The gamma ray frequency decreased by a relative amount of approximately 2 times 10 to the minus 15, precisely as given by the formula on screen. No more, no less. Within measurement uncertainty, the agreement was perfect. That means the null result wasn't confirmed. The frequency changed. The effect was real. The hypothesis survived a rigorous experimental test. Pound and Repka experimentally demonstrated that a photon moving upward in Earth's gravitational field truly loses energy and decreases in frequency. This remains one of the most elegant and precise confirmation of gravitational redshift in the history of physics, an effect of only 2 quadrillions measured unambiguously. A second example of a correct scientific hypothesis comes from the Foucault pendulum. If the Earth rotates, then the plane of a pendulum's oscillations must rotate as well. The rate of this rotation is equal to omega times the sine of phi, where phi is the latitude. If the Earth is motionless, no rotation will occur. Again, we see a precise formula, a direct prediction, and null result as falsification. What did the experiment show? The Foucault pendulum did rotate its plane of oscillation exactly at the rate predicted by the formula on screen. At the latitude of Paris, the measured rotation matched the calculated value within experimental error. The null result didn't occur. The pendulum rotated, therefore the Earth rotates. This was one of the first direct mechanical proofs of Earth's rotation, obtained not through astronomical observations, but through pure physics. How a scientific hypothesis is tested? If the hypothesis is correct, then under the right conditions, we will observe the effect exactly as calculated. If the hypothesis is incorrect, the effect will be absent or will differ fundamentally from the prediction. No vagueness, no approximately, no we'll see what happens. Scientists must clearly specify what effect they expect, how it should occur, and what will be observed if the hypothesis is wrong. A hypothesis can be called scientific only in this case. If it's true, we'll see this effect. If it's false, we'll see something else. That is science. Thank you for being with me on Bold Science with Firuza. It only gets more interesting from here. In the next video, we'll examine the third criterion of a scientific hypothesis, the most subtle, the most philosophical, and the most honest one, the criterion that demands not blind loyalty to the past, but consistency with what has actually been measured. That is why new ideas may overturn old beliefs, but must never contradict facts. Subscribe, like the video, and I'll see you in the next episode.